Today we are going to talk about the topic on rest and motion kinematics. The first topic on this thing is displacement and distance. Now, it appears that displacement and distance, they look very similar to each other, but no, there's a difference. Let us say in XY coordinate, you move from point A, go to point B in this direction, then from B to C, you go in this direction, and then from C to D, you go in this direction. Now, if somebody asks, what is your total displacement from A to D? Or rather, if somebody asks you, what is the total distance you have traveled from A to D? Well, you have traveled, the distance you have traveled is A to B plus B to C plus C to D. You could have traveled in any other path, it doesn't matter. So the distance will still be the actual path you have traveled all along the path. Okay. Now as against this, what is displacement? Displacement is a straight line distance between starting and finishing point. In our case, we started from A and ended at D. So our displacement would be a straight line running from A to B. This would be A to D, right? So the main difference between distance and displacement is, in distance, whichever path you take, the actual contour of the path that you have traveled is taken care. While in displacement, it doesn't matter whichever way you go, you take this path or you take this path, the displacement is always taken as a straight line between first point, starting point, and the end point, right? Okay. Now we define what is velocity and acceleration. Velocity of any point v is given by dx by dt. Rate of change of x coordinate with respect to time, or rather rate of change of displacement coordinate with respect to time. Similarly, a would be rate of change of velocity with respect to time. This is also same as d square x by dt square. Okay. Now next thing we see is motion in a straight line. With constant acceleration. If we start moving from position A and take any path, go to position B, assuming that the acceleration is constant, we can, sorry, this is, we cannot take this example because we are not traveling in a straight line. Let's say we start from A and we move in a straight line and go to point B with a constant acceleration. Constant acceleration doesn't mean that you have to have acceleration. Acceleration could be zero also, in which case your velocity is constant. Okay. Now there are certain formulas which come into play, which is v is equal to u plus at V is the final velocity. U is the velocity you started with at time t is equal to 0. And then V is the velocity after a lapse of time t. And if there was any acceleration, A, which was uniform. It is very important to note that A should be uniform or constant. Then S is equal to ut plus half at square, where S is the distance traveled, U is the initial velocity, T is the time taken, A is the acceleration, and then V square minus U square is equal to 2AS, where V is the final velocity, initial velocity, acceleration is the distance traveled. Now we can easily derive this formula from here. Let's see how. V square we take, for V square we take the value from here, which is U plus 80 whole square. This is U, this is V square. This is equal to U square plus A square T square plus 2AUT. This is equal to U square plus 2AUT plus half AT square, or we can say V square minus U square is equal to 2A. This term was our distance here. Okay. Right. We can also prove these above formulas from calculus point of view also. Let's see how. We know dv by dt, rate of change of velocity, is equal to acceleration, right? Or dv is equal to a dt. And if we integrate dv from initial value of v, which was u, to final value of v, which was v, is equal to integral of a dt from time 0 to time t. Now, if we assume a is constant, we can take it a outside dt. This becomes at, which means, and this integration would be what? V minus u. So what we achieve is v minus u is equal to at. This is the first formula that we saw, right? Now similarly, we know distance traveled is equal to velocity time t, and we take very small distance traveled ds in very small time dt, where v was constant. Okay, this means that we put the value, this actually means v is equal to u plus at, and we put the value of v here, v is equal to u plus at dt. Now we integrate both, integrate ds, s goes from distance 0 to s, t goes from time 0 to time t. This is equal to ut plus half at square. This becomes our distance. So we arrive at the same formula as before. S is equal to ut plus half at squared. And again, we have to keep in mind that A is constant. Otherwise, we cannot take this thing out of integration part. Okay. So far, we have seen motion in a single line, but same laws will hold in more than one dimension also. Let's see how. Again, we have xy axis. Let a particle moves from point A to point B. Now the position vector of point A is this way. And the change in position is this. Let's call it delta R. Okay. Now, if we take this delta R and we resolve in X and Y components, then delta R, let's say we take it C, we put the point, this place A, this was B. So delta R is equal to AC plus CB, right? And if we differentiate this with respect to time, we have to differentiate both these terms with respect to time. So delta R by dt is equal to d by dt of AC plus CB. Okay. Now, this is equal to d by dt of delta x in I direction, this part, plus d by dt of delta y in j direction. Because this was CB was change in position with respect in y direction. Okay, so this is same as dx by dt in I direction plus dy by dt in j direction. Okay, so this is our total velocity. This rate of change of position vector with respect to time gives us v. V becomes this one. Now, this is the formula of velocity if there is motion taking place in I direction as well as j direction. Similarly, if there is a z direction, we can add z component also, exactly the same way. So what we have seen is that total v is velocity in x direction plus component of velocity in y in z direction, right? Similarly, if we take acceleration is rate of change of velocity with time, and we differentiate this equation with respect to time. What we get is differentiation of velocity x in x direction with respect to time is nothing but ax Similarly, this will become our A by J. Okay. So if we write in component form, we can summarize this like this. Vx is equal to ux plus 80. X is equal to these are equations for x component. Similarly for y component, same. Distance traveled in y direction is equal to initial velocity in y direction times t half a in y direction, velocity in y direction square is equal to u square plus 2 ay. If there was another component in z direction, exactly the same thing, right? Now here again keep it in mind that a is constant in each direction. In each direction means I, j as well as whatever their component may be, but the component of acceleration in I direction, j direction, k direction should remain constant. Otherwise, these laws will not be applicable. They are applicable only if acceleration is constant. Okay. The next topic we are going to study is projectile motion. What is a projectile? If we talk about again our x and y coordinate, we shoot a projectile at some angle theta and with some initial velocity u, and let it go in the air. So what happens is it goes in the air like this, goes to the maximum height and then start falling back, and ultimately it touches ground here. Okay, so this is our initial velocity u. If we take the 0 o b, then what are the initial conditions? If we resolve this u in x direction, what it will be? Ux will be u cos theta and y will be u sin theta. Okay. For horizontal motion, Vx is equal to u plus axt, right? and x is equal to x is equal to velocity times t, provided Vx is constant, which it is, because there is no force acting in x direction. Any acceleration, there is no acceleration acting in x direction. So velocity in v direction remains constant, which is equal to initial velocity of v in x direction, which was u cos theta times t, right? And velocity in v direction is initial velocity in y direction minus acceleration, because g is acting downwards against the motion. The projectile is trying to go up, whereas g is trying to go down. So the acceleration is the negative direction, which means y is equal to right. Now we also know that OB, this distance OB is equal to velocity in x direction, which was constant, which was u cos theta into times t. Okay. Whereas y, distance traveled in y direction, this distance would be y is equal to this is the distance traveled in y direction. Now, what happens when we shoot a projectile? Its x velocity in x direction remains same, nothing happens. But what happens to velocity in this direction? Because acceleration is acting negatively, the velocity constantly keeps on decreasing, and at point comes when the velocity in z direction is 0. Here, velocity in this direction is 0. And after that, it starts falling like a free falling body. Okay. So if we say this is the total height, maximum height that it has attained, h. For y is equal to 0. If this is 0, then what happens is ut sin theta is equal to half gt square, or t square is equal to 2 ut sin theta by g, or t is equal to, this gets cancelled, 2u sin theta divided by g. Now what is this t? T is the time taken to make y again 0. Y 0 means it starts from here, y keeps increasing, then y starts decreasing and becomes 0 here. So this time will be total time taken for the particle or projectile to travel from initial position of 0 to P. And the total time taken in this journey is called time of flight. Similarly, this OB has the distance OB has a special name called range. Range is equal to OB. And we know that this will be given by T into velocity in x direction. Velocity in x direction is always constant, which is V cos theta, or sorry, U cos theta, right? Which is equal to time we substitute this time from here, it becomes 2U sin theta by G T into U cos theta. Yeah, this is equal to 2U square sin theta cos theta by G. This part is also called sin 2 theta. Sorry. 2 we have absorbed in 2 sin theta cos 2 sin theta cos theta is equal to sin 2 theta. So what we end up here is U square sin 2 theta by G. Now if you see, this is range. If we have a fixed initial velocity, but we are free to choose our angle, what angle should we choose so as to get maximum range? Which will be when sin 2 theta is maximum. Sin 2 theta maximum can be 1, which means sin 90 degrees is equal to 1. That means 2 theta is 90 or theta is 45. That means if we shoot our projectile at 45 degrees to the ground, if this angle becomes 45, our range will be maximum. We will have maximum range. Okay. We return to our original drawing, projectile being shot at theta degrees from horizontal. Now this time we want to find what is the maximum height a projectile will attain. We know distance traveled in y direction is equal to ut sin theta minus half at square. Okay, let's say this is equation 1. At maximum height, we have seen that v in y direction is 0, which implies distance velocity in y direction is equal to final velocity in y direction is initial velocity in y direction minus at. This is u0 at maximum height. So uy is equal to at. Now, since the projectile, the acceleration acting on projectile is g, so we can also say that this is equal to gt. Or t is equal to and initial velocity in y direction is u sine theta. Okay. Let's say this is our equation 2. Then putting this value, this value in this equation, what we get is y is equal to u half g v square. This is equal to u square sine theta to sine theta by g. This is also equal to so the maximum height attained is equal to u square sine square theta by 2g. So in projectile we have seen three things. And what are these? We have seen time of flight is one thing. Range was another one. And maximum height attained is the third parameter. Okay. So far, whatever we have seen regarding laws of motion in x direction, y direction, or z directions, they are all applicable if the distances, time, height, length, breadth, everything is observed from a stationary frame, which means all the time, height, breadth is observed by observer who's not moving, or even if he's moving, he should not be moving with any acceleration. If the observer is moving, all our Newtonian laws of motion will not be applicable. They are applicable only if all the parameters of time, distance are observed with respect to a fixed reference frame, stationary reference frame, or if this reference frame is not stationary, if it is moving, it should not be accelerating. That means it could be moving with a constant velocity. Okay. Let's see. Here are two reference frames. One is this reference frame, which we can call as S dash, and there's another reference frame with this XY, and we will call it as S frame of reference. S frame of reference has a origin here. S dash reference of frame, S dash reference of frame has its origin O dash. Let us say there is a particle P here. Now particle P can be observed from this reference frame as well as this reference frame. If we observe from this frame of reference, its radius vector is this. If we observe this particle from this reference of frame, then its position vector will be O dash P. Then there is a relative motion between this frame of reference and this frame of reference, which is O dash is moving with respect to O. Now to summarize all these things, let's say what happens is, we can see from the picture that OP dash is equal to O dash plus O dash P, right? Or in terms of position vector, we can also write position vector of P with respect to S is equal to position vector of S dash with respect to S plus position vector of P with respect to S dash, right? Now, if the particle P is moving, let's differentiate both sides. What happens is d by dt of this is equal to d by dt of second term plus d by dt of third term. Okay. Now what is this? This is nothing but velocity of particle P as seen from S reference frame of point. This is velocity of S dash S seen by S plus velocity of P as seen from S dash frame of reference. This red one is S dash frame of reference, and this black one is S frame of reference. O and O dash are their origins respectively. Similarly, if we differentiate it further, what we will get is acceleration of particle P with respect to as seen in S frame of reference is equal to acceleration of S dash with respect to S, plus this is acceleration of P in S dash frame of reference. Now, if acceleration of S dash with respect to S happens to be 0, meaning thereby these two, this frame and this frame may be moving with respect to each other, but they are not accelerating with respect to each other, meaning thereby between these two frames there may be relative velocity which is constant. In that case, what happens is the acceleration observed on a particle from one frame of reference is same as acceleration of this same particle observed from another frame of reference, which may be stationary with respect to, in which case the S and S dash could be either not moving with respect to each other or have constant velocity, meaning there are no acceleration. Then it doesn't matter whether you observe a particle from one frame of reference or from another frame of reference. But if there is a relative acceleration between the two frames, then these two acceleration will not be same, right? So to reiterate once again, as we have seen here, if you observe same phenomena from two different frame of references, all these laws will be applicable, all the Newtonian laws. Will hold true. But if these two frames, two reference frames, are accelerating with respect to each other, then these Newtonian's law will not be applicable at all. The two reference frames, S and S dash, with this we discussed just now, are called inertial frame of reference and non-inertial frame of reference. So S will be called as inertial frame of reference, and we can simply say this is stationary with respect to ground. Another frame of reference, this one, the S dash, which is moving with respect to ground, we call as non-inertial frame of reference. That is, it is moving with respect to ground. For the timing, we forget whether it is moving with a uniform velocity or not. In principle, an inertial frame is one which is stationary with respect to ground, and a non-inertial frame is something which is not moving with respect to ground. All the Newtonian's laws are applicable in this domain. Here, Newtonian rules don't apply. We mentioned that in a non-inertial frame of reference, Newtonian rules don't apply. However, there is one exception, in which is that in case a non-Newtonian, a non-inertial frame of reference is moving with constant velocity, then Newtonian rules will be applicable.